So let's illustrate the numerical solution of second order ODEs by some examples. And so we want to sort of recall the method first. So we are given the second order differential equation, y double prime equals some function f on the right hand side, which depends on independent variable we are now labeling as x, and y prime. Y prime is the derivative of y with respect to x, and y double prime is the second derivative. And we are given two initial conditions for the second order differential equation. The value of the function at x naught is y naught, and the value of the derivative is y0 prime. So these are known numbers, and we are given the differential equation. Reason we chose to represent the independent variable now as x is that often in applications the dependent variable will depend on, say, a spatial coordinate and so on, and so we like to call spatial coordinates x or r or something rather than t, where t we think of as time, but of course we can keep that straight by choosing whatever variable you like to use. Alright, so we are interested in obtaining a solution over an interval starting with the initial point x0 all the way up to some x max. That's the range over which the independent variable varies. And so the steps were that we are going to rewrite this second order differential equation as a system of first order differential equations. And then once we have that, then we're going to discretize them using numerical methods that we have talked about before. So we choose a step size delta x, and so in choosing the step size, it's always good to think about the physical problem. What are the spatial or temporal variations? On what scales do they occur? And we want to choose delta x so that we respect this variation that we are anticipating in the solution. And we also need to pay attention to the numerical stability of this integration that we're going to carry out. Okay, so once we have done that, we are going to start from x equals x naught using the initial conditions, using the step size we have chosen. We're going to integrate, and we can use the first order Euler or the second order Euler method or other schemes such as Runge-Kutta schemes to carry out the integration. And so once we have carried out the integration, we have the numerical solution, and we ought to ask how accurate is this numerical solution that we have obtained. And so for that, we have a practical test where we can choose a sequence of step sizes, delta x's. Different values of delta x can be used to compute the numerical solution, and we can then compare this numerical solution to look for numerical convergence. Is the solution converging as we refine the step size? As we make the step size smaller and smaller, is the solution converging? Because if we really have a good solution, that solution should not depend on the step size. It should become independent of step size. So does it? Looking at that, convergence is something that we need to do. So towards that, we want to quantify the numerical error that the numerical solution we have computed has. And this, of course, is very convenient if we have an exact solution available to the problem. If we have such a solution, we can define error by taking the difference of the numerical solution from the exact solution at the various points where we may have stored the numerically computed solution. We can evaluate the exact solution there. But often we don't have an exact solution because we are solving a new problem, a problem for which analytic solution may not exist or may be too hard to compute. And so then how do we do this in practice? We would use the best available numerical solution as a reference solution. So we don't have YE, but we'll have a best available solution, and we can take numerical solutions obtained with different step sizes, its deviation from the best available, which typically would be the one available for the finest step size that you have. And you can, for example, you can take a very, very fine step size just to compute this reference solution, and then you can take other solutions that are numerically obtained to observe the rate of convergence of this error. All right, okay. So once we have defined this error, we want to quantify the error, and so we can define error norms. We can define 2 norm, which is the RMS error. We can define 1 norm of the error, which takes the absolute value of the error at every point and computes an average in terms of the locations where we have this error over the interval of interest. And we can also define an infinity norm, which takes the worst possible error over the entire interval That's the definition of the infinity norm. So using these norms, we can then characterize how the error behaves as we change the step size. So we're going to apply this now to some examples. These examples are quite simple, and in these cases actually we have analytic solutions available for the examples that we're going to look at, and these examples will illustrate some of the important issues that arise in actual computations.